Good day. I hope you are all well. Today we are going to look at transformer design. Now, a transformer may be designed for maximum efficiency or for minimum initial cost or minimum annual cost, or usual practice is designed for the best efficiency. Now let's look at the main dimensions of a transformer core. We have the cross-sectional area, the window area, low voltage and high voltage windings in the window area, enough insulation for safe operation. We have to look at the design of the windings, the conductor size, the number of turns per winding for a given capacity, and the specifications. Now, basic arrangement of the core and the coils. Now here the core section is taken as circular. The diameter taken as the circumscribing circle of the actual stepped core. There you can see that the windings are arranged so that the low voltage winding is closest to the core and the high voltage winding a little bit further away. Now the main dimensions of a transformer. We have the width of the transformer, the height of the transformer. D is the difference between the center of the limbs. Then we've got the window area, which is the height of the area times the width of the window area. And small d is the diameter of the circumscribing circle. Now the space required to place the coils of the transformer around the core is known as the window space. This is between the limbs of the core and the yoke joining them. Now there's different type of core shapes. A square section, we have diameter of the circumscribing circle, and the side is then 0.71 d, and the area of the iron is 0.45 d squared. If we have a two-step or a crucifix form, then the height becomes 0.85 d, and the area is 0.56 d squared. And so on for a three-step, we've got 0.9 d, where the area is 0.6 d squared. Now the low voltage winding has a cross-sectional area of A2 and a number of turns N2. The high voltage conductor cross-sectional area of area 1 and number of turns 1. Now the area occupied by the coils on both limbs in a window space is a half A1N1 plus a half A2N2 plus on the other side half A1N1 plus half A2N2, which gives us A1N1 plus A2N2. Where the area of the window is the height of the window times the width of the window. The window space factor, area occupied by the winding in the window area, divided by the area of the window. The area occupied by the winding is less than the actual window space due to insulation. Window factor varies with the type of construction, voltage and rating of a transformer, single phase or three-phase core type. In a three-phase core type, we have two windings, two low voltage windings and two high voltage windings. So therefore the window factor is 2 times A1N1 plus A2N2 divided by the area of the window. Now specific magnetic loading. This is excited, the flux is set up in the core. The flux is the flux density times the area. Thus, by specifying the flux, it's possible to determine the cross-sectional area of the core. D depends on the material of the core and the thickness of the laminations. Flux is such that the core doesn't saturate and the losses remain within limits. The maximum flux density is beta, and that lies between 1.5 and 1.6 Tesla. Specific electric loading, Q. This is the current density used in selecting the conductor size of the windings and carry current without overheating, depending on the type of cooling. Tanks with the radiators and tubes, then the current density varies between 2 and 3 amps per millimeter squared. In the design of a transformer, your specific magnetic load and a specific electric load must be selected first. The output equation of a transformer, E is equal to 4.44 flux times the frequency volts. Now that is per turn. Now the core type, single phase and shell type, the copper in the window is A1N1 plus A2N2. Therefore, KWAW is equal to A1N1 plus A2N2. But A1N1 is equal to A2N2, and therefore I1 is equal to J times A1. And IN is equal to J A1N1, which is a half kWj. So the output of the transformer then becomes S is V times I times 10 to the power of minus 3 kVA. And that becomes 4.44 B max, area of the iron times the frequency times the number of turns times the current times 10 to the power of minus 3. So therefore S then is 4.44 B max, area of the iron frequency times half kWAW, and that becomes 2.22 B max AIFJ times 10 minus 3. Now for the three-phase core type, we have the copper in the window is 2 times A1N1 plus A2N2, and therefore KWAW is 4 times A1N1, because A1N1 is still equal to A2N2, and therefore I1 is JAI, and IN is equal to JAN1, which is a quarter of KWAWJ. So therefore S is 3 times VI times 10 minus 3 kVA, and in the end that gives us 3.33 B max, area of the iron frequency KWAWJ times 10 to the minus 3 kVA. For the three-phase shell, there you can look through all these examples again, and there we get the rating is 6.66 B max, area of the iron frequency KWAWJ times 10 minus 3 kVA. The volts per turn differ in transformers of different types and sizes, increasing with size. So if we let flux and IN be the magnetic and electric loadings respectively, and A is equal to F phi over IN, we get S is 4.44 flux IN times 10 minus 3 kVA, which becomes 4.44 over AF flux squared times 10 minus 3. And therefore we get flux is 1 over F times square root kVA times the area times 10 to the power of 3 divided by 4.44. And therefore the volt per turn becomes K times the square root of S. Now K is a constant depending on the material, labor cost, type of transformer, single phase, three phase, core or shell. Certain values for K. Core, single phase 0.75 to 0.85, three phase 0.6 to 0.9, three phase distribution 0.45 to 0.75. Shell 1 to 1.2, three phase 1.1 to 1.15. The three phase distribution 0.8 till 1.25. Design of the windings. N1 or N2 is V1 or V2 divided by the EMF per turn. I1 or 2 is S per phase divided by V1 or V2. And A1 or 2 is I1 or 2 divided by J, which is in square millimeters. Now let's look at design example number 1. We have to determine the approximate overall dimensions for a 200 kVA, 6,600 440 volts, 50 Hz three-phase core transformer with the following data. EMF per turn is 9 volts. Maximum flux density is 1.3 Tesla, not Weaver, sorry. Let's just correct that quickly. J is 2.5 amps per millimeter squared. kW is 0.3, and the height is equal to the width of the transformer, and it's a 3-step core. So S is 3.33 because it's a 3-phase core. F times AI times AW B max J KW times 10 minus 3. Now, if we substitute that into our equation, we get that AI times AW is 1.232 times 10 to the minus 3 square meters. If we substitute that in the EMF per turn, we get that the area of the iron is 0.03118 square meters. Now for a 3-step core, area of the iron is 0.6 D squared, and D is 0.9 D. So 1.185 times 10 to the minus 3 is equal to 0.6 D squared, and then we get the diameter is 0.23 meters. Area of the winding, or the new area of the iron, is then, because of the rounding off, we have to recalculate it. We get 0.23 times to the 0.6. That gives us 31.74. And therefore, the window area becomes more or less 390 centimeters. The width is 390 divided by H. And the width of the transformer is 2W plus 2D plus 0.9D. Or it could have been 2D plus 0.9D. And if we substitute it in there, we get that W is 2W plus 66.7. H is small h, which is 2 times plus 2.9D. And if we substitute that back into our equation, and remembering that W is equal to height, we find that our width and height is 84.4 centimeters. Let's look at example number 2. Design a core for a single phase 300 kVA 500 Hz core type transformer with the EMF per turn 0.6 square root S, kW is 0.3, D max is 1.3 Tesla, J is 2.5 amps per millimeter square, 3-step core, and the distance between the center limbs is 35 centimeters. So if now substitute that, we get the EMF per turn is 10.4 volts. And therefore the EMF is 4.44 FB max AI. Substitute that and we get the area of the iron to be 36.036 times 10 to the power minus 3 square meters. Therefore 300 is 2.22 times 50.36 times AW times 1.3 times 2.5 times 10 to the power of 6. Now remember, we take amp per millimeter to amp per square meter. Then we find that the area of the window is 0.077 square meter. The area of the iron is 0.6 d squared, and there we find that d is 0.245 meter. AW is HW times d minus d. And then we find that the height of the window is 74 centimeters. So therefore, the dimensions of the core, diameter of the circumscribing circle is 24.5 centimeter. The net core area is 360 square centimeter. The pitch of the core centers is 35 centimeter. The height of the window is 74. The net window area is 770 centimeters squared. Overall width 92. Overall height 96 centimeter. And there's a drawing of the transformer. Cool. If we look at example number 3, the area of the window in a 2200/440 volt 15 kVA 50 Hertz single phase transformer is 340 centimeters squared. This window space factor is 0.35, maximum flux density 1.1 Tesla, current density is 2.1 amp per square millimeter. We must estimate the sectional area of the iron in the limb and the diameter of the circumscribing circle around the square core section. Also the number of turns per winding and the conductor cross-sectional area of each. So it's a single phase core type. For S is 2.22, F P max area of the iron times the area of the window, J kW times 10 minus 3. If we substitute that, we find that the area is 54.1 square centimeters. Now for a square core, we have AI is 0.45 d squared, and we find that the diameter of the circumscribing circle is 12 centimeters. The EMF per turn is 1.2 volts, and as always, when we start with design, you always try and calculate the number of turns on the low voltage side first. So then we get 367 turns, and if we calculate the high voltage turn, it comes 1835. I1 is S divided by V1, which gives us 6.8 amps. I2 is S divided by V2, which is 34.1. IC2 is 34.1 divided by 2.1, which gives us 16.25 millimeters square. So that's the area of the copper. And the area of the copper in the primary is 3.24 square millimeters, because that's the current divided by the current density. Now, example 4, we must estimate the suitable number of turns and cross-sectional area per winding per core of 100 kVA, 6600/440 volt 3-phase transformer, 50 Hertz, delta star, core type. Following data applies: 2.5 amps per millimeter square current density, window space factor 0.3, B max 1.2 Tesla, area of the window is 1.5 times the area of the iron. And because it is a core type, it's 3.33 B max, area of the iron, area of the window, JK, W times J. And if we substitute that, we get the area of the iron is 211 square centimeters. Substitute that into the equation for the EMF per turn, and we get it 5.619 volt per turn. So therefore N2 is 440 divided by square root 3 because it's star. And it gives us 45.2 turns, more or less 45. So N1 using KT gives us 1,169 turns. IA1 is S divided by square root 3V, gives us 5.05 amps per phase. And IA2 131.2 is a cross-sectional area of conductor 1, 5.05 divided by 2.5 amp per millimeter gives us 2.02 millimeters squared. And that of the low voltage winding is 52.5 square millimeter. Example 5, we have to evaluate the approximate figures for a net core, cross-section and overall height and width of the frame, B, the number of primary and secondary turns for a 250 kVA, 3-phase, 11,415 kilovolt delta star 50 Hz transformer, core type, by using the following data. EMF per turn is 8.6 volt, Vmax is 1.35 Tesla, J is 240 amp per square centimeter, kW is 0.24, and the ratio of the height of the window to the window width is 2.6. Also that the width of the transformer is equal to the height, and we have a 4-step core. So that the area of the iron is 0.6 d squared, and the core lump width to the diameter is 0.92. Substituting it back into our equation, we find that area of the iron and the window area is 1.931. We substitute that in the EMF per turn, and we get that the area of the iron is 28.695 times 10 to the minus 3. And therefore, substituted back, we get the diameter of the circumscribing is 22 centimeter. The area of the iron, the new one, because of the rounding off, becomes 290 square centimeters. The core length width to the diameter, 0.92, so there we have the window width is 290 divided by H. And then the window width is 2 times W plus 2D plus 0.92D. When H is the same, H plus 2.292. And if we substitute it back, we find that the height is 39 and the width is 7.4. And the width of the height and the width of the height of the transformer is 79 centimeters. N2 is 415 divided by square root 3 divided by 8.6, which is the number of turns per volt. That gives us more or less 28 turns. And then N1 becomes 1279 turns. And then finally, evaluate the no load current of a 6,600 440 volt 50 Hz single phase core type transformer with the following data. Mean length of the path, magnetic path 270 centimeter, cross-sectional area is 140 centimeters, maximum flux density is 1.1 Tesla, the weight of specific weight of the iron is 7,500 kilogram per meter. Specific core loss at the given data is 2.1 watt per kilogram. And the ampere turns per centimeter for the transformer steel at the given data is 6.5. Stacking factor is 0.9. The effective joints is equivalent to that of an air gap of 1 millimeter in the magnetic circuit. So the ampere turns for the iron path is H times L, which is 6.5 times the length, 270 centimeters. And that gives us 1,755 amps. The ampere turns for the air gap is P times L divided by mu naught, which gives us 880 amps. Total MMF, 2635. And the EMF is 4.44 Bmax area of the ion frequency in N1. And we can determine the number of turns, which is 2144. Magnetizing current, remember we are working with the maximum value of the flux density. So to get to the RMS value, you must divide by square root 2. And therefore we get that the magnetizing current is 0.869 ampere. The volume of the core is 2.7 meters because it's 270 centimeters times 126, which is the length. That gives us 34.02 times 10 minus 3 cubic meter. And the mass of the ion is rho times V. That gives us about 255.15 kilogram. Iron loss is 255.15 kilogram times 2.1 watt per kilogram, gives us 535 watt. So the core loss component of the current is then 535 divided by 6,600. That gives us 0.08 amps. So the no load current is IC minus JI naught. This gives us 0.873 at an angle of 84.7 degrees. Thank you very much. Hope you enjoyed that.